So today's lecture we take up the last unit operation of this course, drying. Alright, so far we had absorption, then we started with distillation, extraction, adsorption, and now we have taken this drying here. Okay, so when we say drying, by this unit operation we mean we have a substance, a solid or could be liquid, and we want to remove moisture out of it. Okay, so we have to supply a heat, alright, and then remove moisture to make the substance deplete with the moisture. Alright, for this course what we do here, we try to distribute the course contents. First is like we'll go through the introduction, some examples, alright, then we'll talk about the characteristics of this drying, and it's very typical of different substances. Certain solids will exhibit different type of drying characteristics, so one has to do this experiment or a batch experiment for that type of solid and that type of operating conditions. In other words, if you are trying to scale from a lab to very large scales, some industrial reactor or dryer here, then one has to ensure that we are having similar operating conditions. Okay, so we'll talk about those, then we'll set up the governing equations. How long will it take to dry a solid in batch if you have a continuous process? How much is the length required to achieve that much of separation here? Okay, so again, as you said earlier, that drying for this course, for this unit of operations, we are restricting our discussion to drying of a solid which is soaked with water. We can have different type of inorganics, we can have organics. Sometimes we have say benzene. Alright, so benzene is a vapor and it has moisture or water, and then we give a heat, then moisture can also be removed by benzene. So now that's not drying we are interested here. Adsorptions, we had a very extensive discussion on adsorptions. We have a flue gas, or we can have aqueous water. We bring in contact with the solid charcoals, and then the solute is transferred from water or from the aqueous system or from the gas system to the solid here. So that's also not drying, that's specifically adsorptions. We will see here that certain steps of adsorption, desorptions, they also take place in drying, very similar. But alright, but otherwise what we mean here is we have to give a supply, we have to give a heat to the solid which is soaked with moisture, and we remove this moisture by certain driving force, say partial pressure at the surface and the partial pressure in atmosphere, or the drying here. So with that introductions, let's start this topic here, and let's make a note of few salient points here. Okay, so here we have this drying. This is the last unit operation we have, and a very short definition could be removal of moisture from a substance. Okay, and for this course we will restrict our discussion to solids. So when we say removal of moisture from substance by supply of heat, so we have to give this energy, and by making use of driving force for mass transfer. And this driving force is nothing, we will come to this again in details, nothing but the partial pressure at the surface and the partial pressure in the air stream. So we are talking of a solid surface. So let's say this is some sand or some granules, alright, and this contains moisture. So now when we say that it contains water, this moisture could be inside, in the interior, or this could be covered here with some thin film of moisture. So even one solid, it's possible that there is a film of moisture here. So we supply some heat, Q, either by radiations, or we can have hot air flowing over this, or we can pass the hot air right through this. So we talk about this different method of contact between the hot air and the solid here. So as a consequence of this driving force, so what driving force we are talking here, we have this PS, so partial pressure of moisture in the vicinity of the solid surface and in atmosphere or in this air. So equivalent to this PS, we can think of some YS, some kg of moisture per kg of solid at the solid surface, and here we can have some Y kg of moisture per kg of air here. So that's a driving force. We can also represent in terms of ys minus y corresponding to this ps minus pa. So essentially we have to supply some heat, that's one thing, and we are talking of removal of moisture from solids. Okay, and we said that maybe we can note down that this drawing has a loose meaning. So all we mean that we have to be careful that in our context what we are trying to say here, that the solids like sands, say paper, wood, cloth, some carbon fiber cloth, this contains water or moisture. Now the type of this moisture, which is with the sands or these solids, that could also be different. Maybe this we talked about in case of adsorption, that there are a lot of capillaries or pores within the solids, so moisture can be embedded inside. Alright, moisture can be inside, and some excess moisture can also be on this external solid surface. So both type of moisture, it's soaked, and now we want to remove, so we supply some heat. This could be direct, this could be indirect, so we'll discuss about this. The most common is that you bring some hot air and then remove this to make this dry solid. So now when we say we have the dry solid, here also we have to be careful by saying that, well, initially we had the moisture content was x, say kg of moisture, kg of water per kg of solid, and here we have x1, where x1 is much smaller than this x. So in other words, rarely we will have x1 very small to 0. It's a rare possibility. We will see a lot of limitations, limitation by this because of the property of the solid itself, limitation because of air or certain operating conditions. Okay, so talking about this loose meaning here, so let's say we have saline water, so it contains water plus salt. Alright, so now the salts, relatively it's a smaller, water is a very large quantity, and if you recall some unit operations where you supply heat and then you have this water, which, alright, so water will evaporate, you take this water, condense, and you have some salts left, sodium chloride, etc. Now this unit operation is evaporation, it's not drying. In drying we will see that some step is very close to evaporation. Okay, similarly let's take water and say we have benzene. Alright, now it's possible that we bring this water and benzene in some contact with some solid, let's say we have charcoal. So benzene contains some amount of moisture, so now we want to remove moisture from benzene, we bring in contact with charcoal. This is also not drying. So here we are talking of multi-component adsorptions. Okay, so this would be your adsorptions, although we are removing moisture from benzene. Alright, so different in operations we remove water, alright, but not necessarily it's a drying. What drying we are doing it here again, we are talking of wet solids and we are making it dry solid by supplying heat through mostly say hot air. So this would be the most common scenarios we are going to discuss in this course. Wet solids, so let's say we have zeolites, we have sands, we can have grains. If you recall, in food industries moisture has to be grains to improve the longevity or to ensure that grain does not deteriorate with time. You have a huge dryer where you remove moisture by supply of say hot air. So zeolites, sands, grain, we have some papers, all of this we supply heat through hot air, and then you have this solid which is relatively less wet, or it's a dry solid. Now again there will be some amount of moisture in this, some excess star, equilibrium moisture will be left here, which will be a function of what is operating conditions, air, or even type of the solid. Temperature of course has to play a major role. Alright, so these are different definitions for drying, different applications of drying. Okay, so what here now from the mechanistic point of view, this drawing is, if you are careful, it's about heat and mass transport. So that's the main difference. That's the main difference we had between this drawing and the other unit operations. All right. So if you recall previous unit operations, say absorption, or we had distillations, adsorption, extractions. All of this, most of them, all three of them, other than distillations, we did not have any energy balance or enthalpy balance. All right. The process could be non-isothermal. That's one thing. Say adsorption, certain adsorption could be exothermic, heat may be released, or in other case heat may be endothermic. All right. So in those cases, generally we did not have energy balance. Distillation was one unit operations where we had very extensively energy balance, enthalpy balance. But if you recall, there were two methods. One was Ponchon-Severett and one was Macabeth-Thiele. Ponchon-Severett method was the one where we made very extensive energy balance, enthalpy balance for the top column, for the bottom column. But if you the second method, which we said is much simpler, Macabeth-Thiele methods, it was all based on your species balance, the two operating lines for the rectifying section and for the stripping sections. There was no energy balance except the Q line or the feed line which we had to generate, for which we made enthalpy balance. All right. So by and large, all these unit operations we did, it was extensively based on mass transfer. Drying is one unit operations where you have simultaneous mass and heat transport. Okay, because we are saying that we are starting with the solids, it has moisture, and moisture is removed, so we have mass transfer, either moisture from the surface or moisture from the pores inside. So we have surface transport, say hot air blows over this, so we have done mass transfer coefficients, there is a diffusion resistance. Moisture is also removed, driven off from the pores, so we are talking of now pore diffusion, Knudsen diffusion. Okay, so that's a mass transfer aspect of it, but also you have simultaneous heat transfer. If you want to dry a solids which is soaked with moisture, of course you can bring cold air which has less, it's a less relative humidity than what you have corresponding to this equilibrium conditions. So that will also drive some moisture. All right, but that's a very slow process. We require a very huge amount of air. We'll have to wait long. So generally you have a hot air. So you're talking of now you're heating the solids as well. Okay, so there is some time delay when the solid surface temperature reaches some equilibrium temperature. You can have radiation heating, microwave heating. So different types of heating arrangements. You're trying to enhance your mass transfer by the simultaneously heat transport. Heat also erases your vapor pressures. All right. So the temperature is, there's a film of liquid over the solid, and if you heat it, then the vapor pressure will be larger. Heat content, moisture content is the same. So that you are increasing the driving force for mass transfer as well. Okay, if you increase the solid, bulk solid, then Knudsen diffusivity will also has a function on dependence on temperature. So the diffusivity will also increase. Moisture will be driven off from the pores or from the capillaries. So here we will see that there is very good discussion. We'll have very extensive. This heat transfer has to play a role in addition to mass transfer. Okay, so let's again note down here. So when we say drying, the mechanism here is both heat and mass transfer. So when we talk of heat transfer, maybe we have heat transfer coefficients. So solids blowing hot air either over the surface, or we can have hot air blowing through this. So there is H del T. We can have microwave heating, or let's say we have put a plate on which we have put this solid, and this solid is heated to some temperature T. So by the conductions, heat will be transported. In some cases it happens that we don't want to damage the solid, especially in the food industries, pharmaceutical industries. Very small amount of heat is required. Otherwise at high temperature, if we want to blow with this hot air, then there is a risk of decomposing this solid here. So here we are talking of now minus K del T over del X. So heat transferred by conductions, by convective, or we can have radiations. So we can have microwave heater here. All right, microwave heater, and then by some radiation heating we can heat this solid. So there is a heat transport. Of course we have mass transport. Similar to the H del T, we can have Km del C or del Y, or we can have Ky, and we can talk in terms of pressure, partial pressure difference, what we have at the surface and what we have in the atmosphere. So there is a mass transfer. The most important mass transfer has to play a role in this Knudsen diffusivity. So now we are talking of solid, it has capillaries, pores, so this moisture has to be driven from the inside the pores to the solid surface. So now we are talking of Knudsen diffusivity decay into some concentration gradient inside this solid. Alright, so of course both of them will have an independent effect, but in some cases you can see that heat can improve this Knudsen diffusivity. So it has a simultaneous effect also. We can have unsteady state problems, function of time. So if you start with some solid which is cold, room temperature, now you bring at very high temperature, so it will take some while before this temperature of the solid becomes same as this temperature of your heat plate. So it's a function of temperature. We can have unsteady state problem, or we can have steady state problem. Alright, so unsteady state problem generally you have in batch. How long will it take to dry, to bring the concentration level or solid content or moisture content in the solids from X initial to XF. We can have a steady state problem. So we are talking of some dryer like this. You have granules, you put on a sieve, perforated sieves, and you blow continuously air through this. Or you can have a belt like this. We have some, say, certain coals or certain minerals here, and this belt moves, so and you have the flow of air through this. So it's a continuous process. By hopper you are bringing some minerals here, you are removing it, and you have this hot air. So we are talking of this steady state continuous process. Unsteady state typically you have in case of batch process. Alright, so that's one thing, heat, role of heat and mass transfer. Number two, unsteady state or a steady state. Alright, so these are very introductory matter on this topic drawing. You can go through the textbook Trebol and you can brief yourself about it. Alright, the third thing here is types of solids. Types of solid also have to play a major role, just like we talked when we were discussing on this adsorptions. So here also we can have porous and we can have non-porous. So trying to dry a non-porous solid is different from a porous solid for the same reason that they have large capillaries. So it will take longer time. So when we say drying, we can also have, let's say, sheet versus very thin sheet versus we can have some slab. So notice here we are talking of drying of this sheet and we are talking of this slab here. So in addition to this depth through which the moisture has to be driven off, now also we are talking of some certain area which has been exposed from both end to hot air. So the two we have two different scenarios here. So different type of solids, thin sheets, slab, or you can have cloth. So when you want to dry cloth, say activated carbon fiber, we talked about when we had adsorptions, it contains a lot of moisture, it can soak it a very large porous micropores here. So when you want to dry ACF, maybe you like to wrap this ACF on some tube, right? Tubes could be perforated, you close this end, allow this hot air to pass through this, and then you have air flowing readily outward, alright, instead of taking this ACF and making a back bed. So two will have the different extent of mass transfer or heat transfer. So here we are talking of, when we say types of solid, we are also talking of different types of arrangement. So arrangement of dryers, say like in refrigerators, you have trays, you can have a stack of trays on which you can put solids, and then you can think of hot air blowing past this. In some cases you can have the trays, but this trays will have some sieves, so ensure that the solids diameter is larger than the sieves. So you can have trays like this, and then hot air can blow through this. So it's like cross flow, alright, and here we're talking of, say, surface flow. So two same materials, but the drying rate will be different here. Drying rate will be different here. Drying rate will be different here. So these are the introductory things we talked of. Mechanism, heat and mass transport, that's one. Drying is one unit operations where we'll have both heat considerations, transport of energy, and we have transport of mass, that's one. Different types of solids, so porous, non-porous, slab, thin plates, that's one thing. Different drying rates, maybe same solids, charcoal, but you have one you have made a pellets, one you have made a some thin sheets, one you have made fiber. Different type of dryers arrangements, stacking, okay. Then you have hot airs, in some cases trays, you can have some perforations to allow the air to flow through this. So it's a different type of thing. So then we talked of steady state, unsteady state, just like the previous case. You have a batch, you have a small amount, you want to dry it. You can have a continuous process, so you have talking of minerals or coals or sands, so you have a conveyor belts on which continuously through a hopper these solids they fall on this, the belt moves, and you have air flowing across this, so it's a continuous process, right? So you have a different species balance for or energy balance for a continuous process, and then you have different for your batch studies. What we do now is the way we have our approach has been similar to previous cases. We start with thermodynamics, equilibrium. Absorption, we had the equilibrium, we talked about the solubility, then we had the distillations, we talked about the Raoult's law, relative volatility, then we took up the topic on extractions, we talk of solubility, immiscible fluids, this ternary phase diagram, equilateral diagram. Then we started adsorptions, we had the isotherms, uptake, given so much of partial pressure in atmosphere or in the aqueous phase, milligram per liter, or atmosphere, how much amount of solute is adsorbed by the solid. So Langmuir isotherms, BET isotherms, Elovich, Freundlich. So similarly here in case of drying, also we have this some kind of equilibrium isotherms or equilibrium curve. And what it should be the equilibrium curve? So now we are talking of drying of solids. So we have moisture content. So we start with 1 kg of solid. It has say x kg of water or moisture. Moisture form is also we said is different. We have very excessive moisture, so it will form just like a layer of pool of thin film of water. And once this moisture on the external surface is dried, then now we are talking of moisture within the capillaries, within the pores. So nonetheless, so we have moisture content x kg per kg of the solid materials. So that's on x-axis. And what else we do? Now we talk about this partial pressure. So we are bringing hot air. So it has a very small relative humidity. And what relative humidity we have the surface, or PS, YS. So that's a driving force. So we need to know what type of operating conditions we have, corresponding to that operating conditions, what moisture content we have. Now look at the difference between the drying and the previous unit operations. Their thermodynamic alone, it qualifies and gives you equilibrium curve. Here we are talking of operating conditions in equilibrium. Why? Because what is the equilibrium moisture content? It depends upon what is the hot air compositions, what is the relative humidity of the hot air. Okay. In other previous case, it's an equilibrium. It depends upon the solid and the solutions. We have isotherms ready. So here drying simultaneously also we have some consideration from the operating. One type of solid, right? Same charcoals, but it will exhibit different type of moisture content. In one case moisture content could be large, in one case moisture content will be smaller. We will see, depends upon that also heating arrangements. Okay, drying rate. So equilibrium we have to establish first. We establish the equilibrium, then we talk of characteristics of a very important what do we call drying curve. How does the drying curve change? One has to establish this. So in case of drying, we have some similarity in our approach, but there is a very significant difference here. We want to design a very large dryers for the same solids. One has to do this a small experiment and try to mimic, try to have some analogy between the existing operating conditions and the lab experimental conditions. Okay. So let's start with this equilibrium. So as we said that if you have solids, say let's say some slab like this, or we can have some granules like this, so on which So there are moisture, we can have thin film. Let's start with thin film of liquid, which is water here. Solid also we can have some moisture here like this. So we are talking of P0 minus P or P bar. So what is P0? This we are saying that this is your equilibrium vapor pressure. Alright, equilibrium vapor pressure. So it's a moisture here, and make a note here that this equilibrium vapor pressure need not be the vapor pressure of pure water. So that's another difference we are having here. So what we are saying that if the pure water has a vapor pressure, let's say P0T, say water here, it's possible that the vapor pressure at the solid surface need not be P0W by T. We will see that there are two different ranges. In one case P0 is same as vapor pressure of pure water, and in most of the other cases or different time this P0 is less than vapor pressure of pure water. So P0 like this, it's all it says equilibrium vapor pressure, how much moisture exerts vapor pressure. So again we can think of this in Rawls law like Y P0 into partial pressure. So Y is 1, so equilibrium vapor pressure is what we call here partial pressure minus partial pressure in the air. So this is what we are going to control, is a partial pressure of moisture in atmosphere. Partial pressure of moisture in air or atmosphere. So this P bar, that means it's dependent upon what operating conditions we choose. It's not something which is fixed. So different partial pressure in atmosphere, different quality of air will give different drying rate. So we are slowly getting into this design business, drying rate. So it's characteristics of a drying of a solid here. All right. So that's driving force we are talking. Okay, that's one thing. So when solid starts, now water starts evaporating, as the solids start drying, this P0 will change. So this P0, what we are writing equilibrium pressure, of course temperature is fixed, but now this becomes time dependent, and you have P bar, assuming that P bar remains constant. That means the drying rate is a function of your moisture contents. So we will talk about this, how does now the partial pressure at the solid surface, it changes with time as the solid is getting dried up. So what we will do, or in your lab, suppose you take a solid, suspend it, very simple experiment, and you have hot air flowing past this. So you have some kind of velocity profile. This solid could be, again it could be porous, could be non-porous. You have suspended, maybe you are measuring its weight by some thermogravimetry method. So there are very precise instruments. All right, one can measure the weight as a function of time. So essentially, if you we plot, all right, so we are plotting here x, that's the first important drawing curve, we call it, we have in this drawing. So let's plot x, which is nothing but kg of water per kg of dry solid. So in the later lecture we'll talk about the different ways of reporting this moisture content in solid, wet basis, dry basis. You have some idea earlier, moisture contents. So one is going to measure this. Here what we want to plot is P bar over P0 T moisture. So this P bar is equilibrium partial pressure of water vapor in steam. in stream. Okay, and all we have done, we have non-dimensionalized by this vapor pressure of pure water. All right. So this vapor pressure of pure water given temperature is fixed. Just one way of non-dimensionalizing. So maybe here it's 1. So we are talking of now P bar, equilibrium partial pressure. So at the surface, so water evaporates inside or outside at a solid surface. What is this equilibrium partial pressure? Okay. Now you will expect that if you start with a very large amount of moisture contents, to the extent that the solid is completely filled with the solid. So there is a thin film. So when we say thin film of water, evaporation rate from this water or the characteristics of this evaporation of water is not different if we have pool of water, say even lake. All right. So this water which evaporates, this will exert vapor pressure P0T. We said here P0 is 2, same as the thin film of water which evaporates. So right now this P bar and P0T will be the same. That means we are starting with a very large amount of this X content. You will expect that you are following this line of 1, equilibrium partial pressure of water vapor at the surface here is the same as vapor pressure of pure water. So you will expect that as the moisture content decreases, it's falling 1. Then after some times, when you will see the dry patches, it will start occurring. So some solid surface, maybe there is a wet, somewhere there is a dry, somewhere there is a wet, there is a dry. That time typically if you plot a typical drying curve, this curve will go like this. So this would be your very typical P bar versus P over P0 versus X curve. So let's say this is wood. Wood has very typical this type of feature that for a long time it soaks a lot of amount of moisture here. So for a long time you will see that this one will expect the moisture contents are decreased starting from certain values. So say this 0.35 to 0.3, this partial pressure at the surface can be assumed to be same as the vapor pressure of pure water because it's a thin film here. After that, now the patches starts decreasing. Now this goes below 1, all it means now the partial pressure exerted by this water at the solid at the surface, it has gone below the vapor pressure of pure water. All right. So it decreases, then you have all the way till whatever range. So it's going to decrease. You will expect that when it reaches certain level of partial pressure in atmosphere. So now you're drawing with air, or you're drawing with air here. So this air partial pressure, moisture partial pressure, moisture content in this is fixed. So let's say this value is 0.6. So are we plotting P bar over P0T? You should recall from some other class no, that's nothing but relative humidity, or it's a relative saturations, RH relative humidity or relative saturations. All right. So what we are saying here that this partial pressure, equilibrium partial pressure at the solid surface will decrease, then moisture content continuously decreases till it reaches a level where you have this P bar over P0 is 2 equal to 0.6. Essentially now this becomes your air partial pressure, when the partial pressure of moisture in solid at the solid surface becomes equal to this. So now no matter how long you stop, you have reached an equilibrium. Okay, some solid surface they can have which absorb very large amount of moisture, they can behave like this. Certain other type of solid can behave like this. That means it have very long this extent of moisture. We give certain names here. All right. So we are going to mark certain features or certain terminology. We are going to introduce certain terminology here. So let's say again this is X. We have kg of water. per kg of dry solid. And let's make one curve which goes like this. This is 1 P bar over P0 H2O pure water, like this. We reach corresponding air values. Let's say we call it, it says 0.3 corresponds to the quality of air which has been used to dry this. Corresponding to this we have X star or XE. So we can say that no matter for how long we are going to wait, this content cannot go below this, because here you have air and here you have the solid surface or inside, where you have reached a level of P bar which is same as P0, P of air. Right, so moisture in air has the same relative humidity corresponding to what you have the surface, reaches equilibrium. You can call this as free moisture. So this is the moisture which is free to be removed. Okay. Now notice here that if I reduce the quality of this air from 0.3 to 0.1, I can further dry this. I can come down to this level of 0.2. That means the free moisture which has been removed or free to be removed has increased. All it means now the equilibrium value has changed, equilibrium content has changed from say Xe1 to Xe2. So, or this is what we are saying, that equilibrium concentrations or equilibrium moisture content, it depends upon even the operating conditions P0. Unlike in all those isotherms, we said that once you fix temperature, you have an isotherm ready. So given this, so much is this. Here it depends upon your air conditions, air quality of air, to what extent it has been. In fact, it depends upon the temperature also. Same air, but you have the different solid. Maybe you are heating the solid by radiation heating or microwave heating. So this, in one case temperature is T1, another case temperature is T2, but you have the same quality of air going through this. In this case, partial pressure or the vapor pressure of moisture will be larger than this if the temperature is larger than T2. So in all these cases, moisture content will be different. Moisture content at equilibrium in general depends upon your heating rate. It will depend upon the temperature. It will also depend upon type of solid. Okay, we will discuss this later. Right now we have all we have done. We have defined equilibrium moisture content. We have defined free moisture, and here we can define one more, which we will call it as unbound moisture. And then the remaining we can call it as, right from here to here we can call it actually bound moisture. Bound moisture. So what is unbound moisture? Till you have the vapor pressure same as the vapor pressure of pure water. So this is a region where the solid surface is still filled with very thin film of the liquid. So the water depletes, but only from the external surfaces. Till the end you have, at this range, at this moisture contents, still you have some amount of moisture. Below this, now we are talking of dry patches. Okay. So what we are saying here, that to begin with, the solid has a film of water over this. So the partial pressure is same as the partial pressure of pure water, and then we have this patches of solid, patches of dry surface, they start appearing, and then we have the different type of moisture, which we call it bound moisture. Okay, so we use three terminology here. One is free moisture. So this would be X, start with X, and we have Xe, that's one. When we talk of unbound moisture, so unbound moisture, here we are saying that the vapor pressure of at the surface is same as vapor pressure of pure water. So all we are saying that is still there is a film of moisture, film of water. And third, we are talking of this bound moisture. So when we say bound moisture, now the vapor pressure at the solid surface is now smaller than the vapor pressure of pure water. Of course, we have talked of equilibrium moisture. Equilibrium moisture content Xe. So we'll come back to this again. One very interesting thing occurs in case of drying of the solid is, since we have here pores, so the rate of drying is different when we have dry solid and then we are trying to wet. That's one. And when we have the wet solid and then we want to dry. Okay, so in other words, if you have a solid, say the moisture content is X1, we dry it, we bring down to the level of X2. In one case we start with X2 and then we start to wet. Okay, so we bring in contact with moisture and we bring from X2 to X1. So between the two levels, one is the drying X1 to X2 and one is a wet. In terms of in case of this solid, on this drying of solid, what happens, there is a hysteresis. Alright, so that means the path to go from X1 to X2 is different from X2 to X1. Okay, so for the same partial pressure or the same quality of air in which the solid is brought in contact, you will see that the two different moisture content levels. So let's try to understand what we are saying here, that in case of drying we have this hysteresis. We will see that why does it occur. So what we are saying, that if we plot X, what we did earlier, versus this partial pressure over partial pressure of pure water, which is nothing but relative humidity, nothing but relative saturations, and then we say the drying, if you saw this earlier curve, it's like this. Of course it will stop when you have this equilibrium concentrations Xc, given this quality of P bar over P0 is 2 in air. So let's say this number is say 0.3. So now when we dry, we go like this, and we want to wet, then we have the different path like this. So this is all about hysteresis. Alright, so one path for drying, moisture content decreases, and one path for wetting. This is very similar to, say, we are saying that it's evaporation, and here we are talking of condensations, so it's getting wet. Or very similar to, we are saying that it's desorption, there is a desorption, and here we are talking of adsorption. Alright, so what is significance here? If you have a solid which has been dried to this level of P air and we have this equilibrium concentrations, no matter how long you wait, this concentration is not going to go below this. But when you want to wet, then it's not going to follow this path here. Now it has a different path to follow. Or for the same quality of air, now look at this equilibrium concentrations, now it is different. So for the drying there is a different equilibrium concentrations, and for the wetting there is a different equilibrium concentration. A solid which has been dried to this level, when exposed to the same quality of air during the wet, will exhibit different amount of moisture content. Or a solid which has been wetted with this with one quality of air, and now when you want to dry, then it will have different equilibrium concentrations. So this also has some practical applications. From mechanism point of view, why does it happen? If you recall some knowledge of this thermodynamics, you have these pores. All right, so when the pores are empty, so we are talking of now wetting, what happens? The films or the walls start getting filled up here. So there is adsorption. Recall in Arduino, adsorption is very similar to what we call condensation or wetting. So moisture starts getting adsorbed on the walls of the pores till there is a filling. Then of course this gets narrower, and you have the filling like this also. So you have the sideways filling to start with, then it picks up, then the adsorption picks up, and the pores get filled up this way. But when the pores are already filled up, so you have situations like this. Now when you want to dry, then you can see the drying takes place from the surface till at a very small levels. Now we have some meniscus like this, and then we can think of sideways of drying here. So the mechanism of wetting and the mechanism of drying in case of pores of a porous solid is different. That results in the in hysteresis. Whenever we have hysteresis in any context, that means there is a mechanism of certain phenomenon in one path is different from the other path. So here we have the pore filling, which goes sideways. When we have drying or desorptions, it takes place laterally upward. So the mechanism is different. That's why you have two different rates. It's called Kelvin's effect. In fact, Kelvin's equations to calculate vapor pressure or partial pressure in two cases are different. When the pores are filled, what for the adsorption and for desorption, the two are different here. So now what we do here, after we understand this P versus X diagram, we will have some definitions for different ways of representing moisture contents or different quantities here. One is, of course, very important, is moisture content. How do we represent? There are two ways of doing this. One is wet basis, one is dry basis. So when we say wet, we are talking of x kg of moisture or water per, say, 100 kg of water plus solid. So it's a wet basis. And when we say dry, all we have x kg of water per, say, 100 kg of solid. So again, you see the advantage often working on this dry. Solid 100 kg, this remains the same, denominator remains the same. Otherwise here this quantity, both numerator as well as denominator changes because amount of water changes. So there are two ways, one is the wet basis, one is the dry basis. We talked of equilibrium moisture. So when we have equilibrium moisture, we denote by x star. This is like x star. So we are saying moisture content. Again, this content could be dry basis or wet basis, content of a solid when at equilibrium with the given partial pressure of the vapor. So this equilibrium concentrations, we talked about that drying curve, when it goes like this, but it stops at x star. Why it stops at x star? Because now the moisture content of the solid is in equilibrium with the partial pressure of this vapor in the air which has been used to dry this. Okay, so we cannot go below this. If you want to go below this, one has to have a drier air which will take you below this range. We talked about bound moisture. And we talked of unbound moisture. So maybe that's number 3. So unbound moisture, the partial pressure of this moisture, partial pressure of vapor at the solid surface is same as P0T, this vapor pressure of pure water. Alright, so, or in the words, the vapor pressure exerted by this moisture is same as vapor pressure of pure water. So what you are writing here is a partial pressure equal to y into P0. Y is 1 pure moisture, no other species here we have, and this vapor pressure what it exerts, it's same as the vapor pressure of pure water. Okay, so that's unbound moisture. So this will happen when there is a thin film of this liquid, thin film of liquid. Once we talked of when the moisture starts, the whole surface gets dried up, and we're talking of moisture driven off from the pores or capillaries, there it happens that the partial pressure, let's say this is equal to P0, but this P0 will be now less than vapor pressure of pure water. So now we are talking of some capillary effect, etc. We talked of free moisture. So that's moisture which is free for the removal, x minus x star. And of course x star depends upon so many things. It depends upon type of solids, depends upon drying rate, depends upon quality of air, depends upon temperatures. So this is the moisture which is available. We must not we must understand that solid alone is not good enough. We have to specify even the operating conditions when we can say that this moisture is available for removal. So it's only a free moisture which can be evaporated or it can be removed. Okay, and all of this for the last time we draw again. This is the first very important curve, very typical curve we have, where we plot x, kg of water, kg of moisture, per kg of solid. So this is moisture content. Here we are plotting relative humidity or relative saturations or partial pressure of water vapor in air over vapor pressure of pure water. Okay, then we have certain curve like this, which we can draw like this. So let's see, here we mark this line. All right, this is say x star. This contains, this is equivalent to P air we write here. That's the quality of air we have, P H2O T. So this is equivalent concentration we have marked. This is 1, that means partial pressure is same as vapor pressure of pure water. So this would be unbound moisture. And anything below this is bound moisture. Of course, not all bound moisture can be removed or free for removal. That means this quantity here is free moisture. X minus x star. All right. So these are the important things we have marked here. This is the very first thing, first graph, which we need to understand in this drying operations here. All right. Now let's see. Let's try to understand what happens when we have this unbound moisture. All right. So what happens here when we have unbound moisture? We're talking of film here, water film. So the mass transfer rate is, you can expect this should be equal to Ky. Let's say there is airflow here, Ky into Ys minus Y. So what is this Ky first? This is the mass transfer coefficient. So water evaporates. We have done earlier. The moisture on the solid surface, it evaporates. There is airflow. So there will be some concentration gradient. This Ky is a function of Reynolds number, Smith's number, depends what number, what velocity we have, etc. What is Ys? Ys, we are saying that it's a moisture content in air, all right, at the solid surface. So we have pool of the liquid at the top of this water which is evaporating. So this is evaporating water. We have evaporating water, and this Y is Y here, this water content in air. This is very similar to, maybe we can say Kp, we can say that P at solid surface minus P of air. Okay, so this is at the P at the surface of water. This could be equal to, for in our case, when the water is solid surface is covered with the film, this PS will be nothing but vapor pressure of pure water. So it's a constant. As long as you maintain this temperature, temperature is fixed. As long as there is a water film, this is P0T, Reynolds number is fixed. So this is also fixed here. This is also fixed because temperature is fixed and there is a film of water. Ensure that you have continuous supply of air and the content in air does not change. So you have essentially constant rate of evaporations, constant rate of evaporation, which we are calling it as drying rate. So that's stage 1. We have addressed this one. When the rate moisture content decreases from x to certain quantity, let's say xc, let's call it critical moisture content. So this is a zone over which you have unbound moisture. All the time equilibrium vapor pressure is same as the vapor pressure of pure water. Now we have decreased. So now we are talking of the second level where we start decreasing below x. Okay. So now x is less than xc. What happens here? Now the solid surface, now there are dry patches, dry patch of water. Now here if you look at, if you talk of rate as kg of water per meter square of solid surface per second. So now we have to be careful what meter square we are talking. Suppose we start with say 1 meter square of a solid surface which is completely filled with water. Okay, and after some time when x has gone below xc, now we have certain patch, dry patch, but still we are reporting this rate in as per meter square of the total area. That means from individual those areas, regions where there is a film of water, the specific rate will still be the same as what we have here. In other words, the intrinsic rate does not change whether we have full surface occupied by complete moistures or we just have one solid surface where there is small amount of water left here. If we take this meter square and if we take only this meter square, then the two rates should be the same. Alright. So still when you measure per meter square, then there is a possibility that, or then this will happen, that n will decrease. So you have to be careful when we say that when the rate decreases or the rate does not decrease, because it depends upon how you are reporting this rate. In general, you start with meter square of a total solid surface area, which is fixed. So even if there are dry patches, still you report your rate, how much kg of moisture decreases in 1 second per 1 square meter of this. So in that case, n will decrease. So it's, you can say that there's an artifact of reporting here. All right. So what we do here, that one curve we will like to continue in the next class. So if you do this experiment, you have suspended the solid and measure how does this moisture content decreases. Then what you will expect that here also you will have several regions. There will be one region where x will decrease linearly, then it will slow down, then it will further slow down. So next time when we meet, we will mark these points A, B, C, D here. We will call it constant rate because x changes linearly. So if n we define as SS over surface area, total surface area as dx by dt, since x changes linearly, we will expect that this n is constant here. So this range, this region is called constant rate drying. Then of course x changes non-linearly, so that in that type n will decrease here. So we will stop here. Let's just summarize today's lecture. We started with this unit operation, drying, where we are saying that we are interested in drying of a solid. It contains moisture. We want to remove dry bulk moisture from the solid by simultaneously giving heat and mass transport. So we have dry air as well as we have hot air. So there is an effect of both heat transfer and mass transfer. That's the unit operation drying we are saying. Of course, it has a loose meaning, moisture driven off from different substance by say centrifuging, by mechanical separations. That's not drying we are interested. A water, saline water, sea water, you dry off moisture by evaporation. Very large quantity of water is removed. That's evaporations. So that's a definition for drying we are interested here in. That's one. Number two, we talked about drying is one phenomenon where you have so many other considerations like type of solid. One solid, of course, porous, non-porous, but even the way you make the solid pellets, sheet, okay, slab, that will also affect your drying rate. because the operating conditions, external air in contact with the solid surface plays a major role. What is the Reynolds number? What is the quality of air? Do we have entire area exposed to the same amount of air? Or if you're doing a microwave heating, then does the entire surface gets heated? If you have a sheet exposed to microwave heating, and if you have granules which are inside deep, solid surface, may not be get heated by the same, it may not be receiving the same amount of energy. So the drying rate will be different, although you have the same materials. Then we talked about trays, different ways of heating it, cross flow. You have flow over the surface. It's, as I said earlier, it's recommended you go through the textbook and see physically, or some handbook on drawings, different type of trays you may have seen in some unit operation in SAM lab class. Okay. Then we talked about the first characteristics curve of this drawing here. When we plotted X, or we plotted partial pressure of equilibrium partial pressure of moisture over non-dimensionalized with vapor pressure of pure water versus moisture content. And there we said that we have unbound moisture, then we can have bound moisture, free moisture, equilibrium moisture. Then came the definition for the rate. We have to define a rate. So rate we defined as kg of moisture per second per meter square of the area. What area is this? This area is a total area. Alright, not the area of the wet, because this wet area will change. So, but no, we are defining it, we are reporting this rate per meter square of your total area. And then we will see that what does it cause the effect. In between also we talked about this Kelvin effect. Drying has a very special property, very special characteristics, hysteresis. That means drying is different from wetting. If you want to dry a solid surface, moisture content will decrease, it will take one route, different rate. When you start wetting up, putting this moisture here, just reverse the conditions, then we'll take a different rate. That means for the same quality of air, moisture content during drying and moisture content during wetting will be different. This will have, you can make out, this will have a significance if you're trying to say dry or wet certain food packages. Okay, so when you dry in one condition, so you pack it, but you bring to the same quality of air, right, during the wetting. So you start from lower to the higher, you will expect that moisture content will change. All right. So that's the introductions on drying. Next time when we meet, we continue with our discussions on different type of characteristics curve, especially we have drying. Then we take up some few examples or set up the governing equations for unsteady state process.